All right, so today we're going to talk about Chapter 10. This is the last chapter that you will be assessed on for the final exam. And Chapter 10 is correlation and regression. So for many of you, if not all of you, back when you took Algebra 1 or Algebra 2, this was something that was covered. And basically when we're talking about correlation and regression, we are saying that our data, when plotted on a graph, has what we would call a linear representation. It doesn't mean that all of our data points fall on one line, but it does mean that if you were to zoom out on the graph, those points would form something that would look like it has a linear behavior, or it might form some sort of a line. So I have scissors that I'm going to show you later of that. Right now we're just going to go through these slides, and then we're going to go through some notes, and we'll take it from there. So basically, if the value of y is completely determined by the known value of x, the relationship between the variables is what we call deterministic, meaning we can determine what it's going to be. Okay, we can essentially guess, because if we have a line, we can say, okay, if x is this, then y is going to be this. We can determine it. And so this equation right here helps us to understand that this is in fact deterministic. Okay, the relationship between x and y is called a linear relationship because the points so plotted all lie on a single straight line, right? So if we were to look at this, the number 9 in the equation y equals 9x plus 3 represents the slope, right? We would call this y equals mx plus b. 9 would be m, which would be the slope. B would be 3, which would be the y-intercept, okay? And the y-intercept, all that does is really identify where our line is going to cross the y-axis, okay? So basically here, we just have a table, a typical table, and we have those points that we can plot. We have a value for x, a value for y. Negative 40, negative 40. These are ordered pairs. Negative 15, 5. 0, 32, 20, 68, 51, 22, right? Those are ordered pairs. Those can be plotted on an XY coordinate plane. Now, if we were to take a look at this graph right now, we would say that these points are somewhat scattered. They are not all in a straight line. However, what we could say is that these points are exhibiting a linear representation. So as they're aligned, if we were to back off of this, if we were to zoom out, perhaps the further and further we zoomed out, the more and more this collection of points, because I am assuming that to the top right and to the bottom left, that there's more points continuing somewhere around here. But if we were to zoom out, that it would look very, very close to a straight line, okay? And that's where our linear correlation comes into play, all right? So we would say that there is a linear relationship between the variables. It's not, in fact, deterministic, right? We can't determine what that value of y is going to be given the value of x because there's not one line. However, we can say that it is estimated in such a way. This is in many ways kind of like an estimation that these points represent a linear representation. So it says a plot of the data, as shown, right, is called a scatter diagram or a scatter plot. Looking at the plot, it is evident there exists a linear relationship between the height x and the weight y. I didn't talk about that, but basically they're saying that the x values represent the height and the y values represent the weight of people. And if you were to plot those, maybe, just maybe, I'm not saying this is true, but maybe they represent, or their organization of points is a linear representation, okay? The points appear to be following the line, but not exactly, right? So right now we're going to talk about something called the correlation coefficient. And what the correlation coefficient does for us, it represents the variable that we use would be r to determine the correlation coefficient of a collection of points. Basically, what that correlation coefficient will tell us is if our collection of points is pretty close to being a linear representation or if it's really not close at all, okay? Furthermore, it's also going to tell us if our linear representation happens to have a positive slope or a negative slope, okay? Obviously, a negative slope would be starting down in the bottom right-hand corner and going up to the top left-hand corner of a graph. And a positive slope would mean that our line is starting in the bottom left and going to the top right. The way I look at it is if you're walking up a hill, are you walking up a hill in a positive direction or are you walking up a hill in a negative direction? If you're walking up a hill in a negative direction, right, then that would represent a negative slope. If you're walking up the line or the hill in a positive direction, that would represent a positive slope. So to calculate the correlation coefficient, this is basically our formula for that. And they tell you how you can get these values. There's actually 3 pieces within here. They call it SS sub XY, SS sub XX, SS sub YY. Notice we multiply these values together and then we take the square root of it, and then whatever that is, we divide SS sub XY by it. Okay? Now down below here, they're telling you SS sub XX is equal to the sum of all your x values, right, squared, minus 1 divided by the total number of x values times the sum of all your x values, and then you square that in its entirety. So you would do that for this to get this value. This formula is a little bit different. The sum of the x values times the sum of the y values divided by, or times 1 divided by your total number of values, okay? And then this is just the sum of the x times y's, right? And then this, if you're having trouble understanding the Riemann sum, the summation notation, that's something that you're going to need to review. But to this point, because we did use summation notation when we were talking about the calculation of standard deviation back in chapter 2, you all should be in a pretty good space here, okay? So this is just a more in-depth understanding of what the correlation coefficient tells us. Basically, and this is what I already told you before, that if the value of r lies between -1 and 1 inclusive, right, then we can, well, I'm sorry, not if. The value of r will always lie in between -1 and 1. It will always lie there, okay? The sign r indicates the direction of the relationship. Basically, you know, if r is less than 0, meaning it's negative, then it tends to decrease. This represents a negative slope. If r is greater than 0, which means r is positive, that's going to represent a positive slope. So y tends to increase as x increases, right? That's all that is positive and negative slope. This is the explanation of a negative slope. This is the explanation of a positive slope. And then it says the size of r, the absolute value, whether it's negative or positive, if it is very close to 1, then we can say that it has a strong linear relationship, meaning these points, yes, they do have a very strong linear relationship. If it's closer to 0, then we would say that the linear relationship is much weaker, that it really doesn't have a linear correlation, okay? So in this particular example, they're just taking a collection of points. So this would be an example that we would work through here, and we would compute the linear correlation. So the next slides are going to help us to, in fact, compute that, okay? So here, what's nice when you do this is if you take all your x values, you take all your y values, and then you can go ahead and you can figure out this. You can actually use your knowledge from Excel to work through these problems here. Because if you were to put all the values in for x, this would be an ordered pair, 68, 151, right? And then if you went ahead and created a formula to calculate x squared, a formula to calculate x times y, and a formula to calculate y squared, and then summed them up, this would be the summations of those. And you would be using that essentially in your formula over here, right? Notice the values that we're plugging into here represent these values down here. So if you want to take some time to compare those values, you can go ahead and do that and see how they exist in here. And so therefore we can get our values of SS sub XX, SS sub XY, SS sub YY, all right here, plug them into the formula, and then we figure out for this particular set of data, our correlation coefficient, R, is equal to 0.868. This is a positive value, which means it has a positive correlation. It's a positive slope. Our line is going from the bottom left-hand side of your graph to the top right, walking uphill in the positive direction, positive slope. And it's a value that is pretty darn close to 1. So therefore, we could say that this is a pretty strong linear correlation. Okay? Just this other piece here, and then I'm going to move to my paper to talk about it a little bit more. So basically, This equation represents the main, or the determinant part of what we're talking about here. So this, b sub 1, beta sub 1 would represent your slope, b sub 0 would represent your y-intercept, and then we have this value e here. What e represents, and I don't know if they use the term here, but e represents epsilon. Okay, epsilon is a value that is known to mathematicians as being an infinitely small number. Okay, so basically that epsilon represents how our graph may shift one way or the other based off of that correlation. Okay, so this just explains a little bit more. All right, remember, this is what I said is the deterministic part, but when you add the epsilon to it, that creates a little uncertainty. It says that we waver a little bit. Since we know that we can determine, if we're given an x value, we can determine the y value, this part helps us to do that. But this, plus e, this e value here, this epsilon, represents that slight shift in our graph based off of a number of things. And this graph here kind of shows that. So this could be our line of best fit, but we could say that epsilon is going to shift this one way or another based off of those other factors of how different our data points might be.